Today we're going to talk about MIL standard 1553 over Fibre Channel, or what it's also known as is FC-AE 1553. Again, talking about FC-AE 1553 today. What that is it's the core signaling and control protocol used in HS 1760. So it takes the place of MIL standard 1553, which is the core signaling and control protocol of legacy MIL standard 1760 weapons bus interface. Really high level agenda. What we'll talk about first, the Fibre Channel frame headers, so the header fields in the Fibre Channel frames that are used when the FC-AE 1553 upper level protocol is used. And then we'll look at NC to NT transfers, so the analogous of BC to RT transfers on 1553. We'll look at NT to NC transfers, and then also NT to NT transfers. Try to keep it to about a half hour today. And again, this is the second of a multi-part series on this. We'll have another one coming probably right after the first of the year, continuing on the topic of high-speed 1760. A little bit of review from the first presentation that we did, just to kind of reset, because we're building on that a little bit today. So Fibre Channel follows the OSI model, so a multi-layered protocol, building up from like the physical layer to link layers all the way up to upper layer protocols on the top. With Fibre Channel, there's also a hierarchy of the data. So you have the frame layer, so the frames of data, frames built up of the bits and bytes that are sent across the links. And then multiple frames can be combined into sequences of data that are sent across the Fibre Channel links and networks. And then multiple sequences can be combined into data exchanges between two communicating nodes on the Fibre Channel network. So that's the hierarchy of the data. Then if you look at again, this is review from the last presentation and webinar, the frame format, a Fibre Channel frame. So between frames, you have idle frames. So there's always some kind of communication going on. So there's idle frame patterns that go on when no data is actually being exchanged on a link. Then you have a specific pattern that indicates the start of a frame. And then you have a 24 word frame header. This is the contents of the frame header. We talked about this last time. Kind of the major points of this is you have a source ID and a destination ID, which indicate the address of the source port and the destination port for the frame. And then when we talk about the data hierarchy, you have a sequence ID and a sequence count. So the ID would identify the sequence that the frame belongs to, and the sequence count would indicate the order of that frame within the sequence. And then when we talk about the next level up, the exchange, you have the originator of this exchange, the ID that identifies the exchange from the respect of the originator, and then the responder, the other side responding in the exchange, that's that node's ID for that exchange. You also have a type field that indicates the upper level protocol that is being carried within the payload of that frame. You have a CRC to keep the integrity of the data calculated over the payload and the header of the frame, and then a pattern that signals the end of the frame. FC-AE 1553, it's Fibre Channel avionics environment upper level protocol. It supports a real-time bidirectional communication between two or more endports. So it's describing a protocol between two nodes in the network and how they communicate in a bidirectional communications. It's based on the command response protocol originally defined in MIL standard 1553. So it looks a lot like 1553. It's meant to support the same types of applications as 1553. It's meant to be real-time and deterministic and resilient and provide very reliable communications. But it also has extensions because it's on a much faster network, higher bandwidth, right? So 1 megabit per second in traditional 1553, we're on 1 gigabit or maybe even a 2 gigabit network with Fibre Channel, a larger address space, and a lot larger data transfer sizes. So if we look at kind of some of the comparisons here, so what you would call a bus controller in 1553 is referred to as a network controller on FC-AE 1553. A remote terminal is referred to as a network terminal. An RT address is a network terminal address, RT subaddress, network terminal subaddress. What is a MIL-STD 1553 message is referred to as an exchange in FC-AE 1553. A command word is actually a command sequence, so it's a command sequence of fiber channel frames. The status word is a status sequence. When we talk about the address spaces and the data sizes, an RT address is analogous to an NT address, which is in the source ID or destination ID. So you have 24 bits where you only have 5 bits in MIL-STD 1553. And a subaddress is 5 bits in MIL-STD 1553, and then you have 32 bits in FC-AE 1553, and then where you have 5 bits for the data length, you have 32 bits in FC-AE 1553. I do see a hand up with questions. Since it's just me today, if you can type your questions into the chat, I'll try to answer them as I can here. I think that's Nick. Looks like it's asking a question. So yeah, if you can just type them into the chat, I'll try to glance over and answer them. Next, we'll look at some of the specific fields in the frame header for a command sequence. So I'm showing here at the top, this is actually the frame header and the specific fields that FC-AE 1553 uses in the fiber channel frame header for a command sequence. And then below that, I'm showing the command word on a traditional 1553 command word and showing some of the comparisons between the two. So first, you have the destination and source ID fields, which is where the NT and the NC addresses are. So that is analogous to the RT address in a 1553 command word. So for the network controller is going to originate a command. So the source ID is going to be the NC address, and the destination ID is going to be the NT address in a command sequence. Then also the type field, like I said previously, the type field in the fiber channel frame header, that indicates the upper level protocol. So that's going to always be coded as 48 to indicate FC-AE 1553. Then you go down to word 7 and 8 in the fiber channel frame header. That's the subaddress, which is the same as the subaddress mode in the 1553 command word. So that's indicating the subaddress, or it can also indicate that it's a mode code. And then in word 8, you have the byte count, which is the same as the data word count in a 1553 command word. Then if you look at the bit fields in word 6, you have much of the same bit fields that you have in a command word. So you have the transmit receive bit, which would indicate if it's a transmit command to the NT or a receive command, just like you have bit 10 in a command word. Now we get into some of the different things, or the additional features or extensions that you're offered with FC-AE 1553 that you don't have in MIL-STD 1553. So the first thing is the concept of data pacing. So with standard 1553, as an example, if you're doing a network or a bus controller to remote terminal transfer, the way that happens is the bus controller is going to send a receive command word to the remote terminal, and then it's just going to immediately follow that with data words, a stream of data words that the remote terminal has to be ready to receive and then receive. With 1553 over fiber channel, obviously you can send a much larger stream of data, megabytes of data. So there's a possibility that you have to pace that data. You can't just necessarily send a megabyte stream of data to a network terminal and expect it to be able to buffer and receive all that at once. So there are data pacing bits, NT burst size request and delay NT burst size request bits. And what these allow the network controller to do is to say to the NT, hey, I have a lot of data to send, so I'm going to set this burst size request, which is basically telling the network terminal to respond with a status word to tell the network controller the maximum amount of data that the network terminal can receive in a burst. So it basically allows the data to be paced. So we'll look at this when we look at and talk about it a little more when we look at a network controller to network terminal transfer. But that's what those two bits are that I'm indicating with the dot with a 5 in it there. Then also, because we can move such large amounts of data, the bits 5 and 6 of word 6 there are also used to indicate DMA transfers or RDMA transfers. So as an example, if bit 6 is set indicating receive DMA, and then the TR bit indicates receive to the network terminal, that's indicating that we want the receiving network terminal to receive a DMA transfer. And so what that would indicate is that the subaddress word 7, actually indicates a base address in memory in the receiving network terminal where the stream of data is to be written in contiguous memory. So it's indicating that we're doing a memory transfer at the base address that is indicated in the subaddress word of the command sequence. And then vice versa, you can do a read, or basically instruct the network terminal to transmit from the base address indicated in the subaddress word by setting the transmit RDMA bit and indicating transmit in the TR bit of word 6 there. So that's an example of one of the extensions for doing mass data transfers that FC-AE-1553 provides. Next, we look and compare the status sequence to the status word in 1553. Oh, sorry, I have to go back to one thing here. I didn't explain word 9 here. So you actually see a status word in word 9. So we'll look at this when we look at NT to NT transfers. But when an RT to RT transfer happens in 1553, what happens is the bus controller sends a receive command to the receiving RT, followed by a transmit command to the transmitting RT, and then the transmitting RT immediately sends a status word on the bus before it starts transmitting its data words. This is the reason that this command sequence also has a status word in it, because what happens in an NT to NT transfer is first the network controller sends a command sequence to the transmitting network terminal. That network terminal then forwards that command sequence to the receiving network terminal, but it has to then put its status word in this status word of the command sequence before it forwards it to the receiving network terminal. So that's what this status word is in the command sequence. So when we look at the status sequence header, this is analogous to the status word that's sent on standard 1553. You can see that here indicated by the 1 that you have the same status bits are present in the status sequence that are available in the standard 1553 status word. Obviously, the RT address would be analogous to the source ID and destination ID, where the NT and NT addresses are, just like in the command sequence header fields. Then there's some additional fields. So the blob 2 here is indicating these fields that are actually used by 1553 to fiber channel bridges. I'm not going to discuss those, just kind of indicating there that there's built into the spec, there's the concept of a bridge between a standard 1553 bus and FC-AE-1553 network, and there's some fields in here to indicate that. That's a whole nother topic for another day, but that's what those fields are. And then there's also this field for a burst size acknowledge. This is the field in the status word that is basically the other end of that data pacing. We'll talk about that when we talk about the NC to NT transfers, but this is basically how the NT responds when it's acknowledging and providing back the number of data bytes that it's able to receive in a burst when requested by the NC. So it sets that bit, and then it puts in word 7 of the status word, the status sequence, how many bytes it's able to receive in a burst. And then also number 4 here, this other bit field that's outside of the normal status bits. This is a port login required. This is also a little bit of a topic probably that we'll cover in the next webinar after the first of the year. So with Fibre Channel, when at startup, a node on the network has to do kind of a login to the network. It's kind of analogous if you're familiar um, with Ethernet. You have to do things like address discoveries like DHCPs and ARPs to determine your port addresses and the MAC and IP addresses on an Ethernet network of other nodes on the network so that you can communicate with them. So there's the same kind of things have to happen on a Fibre Channel network. So an N port has to log into the F port on a switch, and then an N port also has to do a login to the other N ports in the network that it wants to communicate with. So what that bit is used to indicate in an NT-NT transfer is the NT that is transmitting to another NT. It may have to indicate back to the NC that it first has to actually do a login, that it hasn't logged into the other NT to do the transfer yet. So that's what that bit is for. But that would be a topic for another day when we talk about this login process in a future webinar. All right, so now let's actually talk about some data transfers here. So at the top, I have kind of the sequence of what happens on a standard MIL-STD-1553 bus controller to RT transfer. So what you would have happen first is the bus controller is going to issue a receive command on the bus to the remote terminal. Then it's going to follow with the stream of one or more data words. And then the remote terminal, after it receives, is going to issue a status word that's going to indicate to the bus controller if it received it or if there was errors. Basically indicate the status of success or not. So if we would do something analogous on FC-AE-1553 network, so you'd have a network controller to NT transfer exchange with no data pacing because you don't have data pacing on 1553. What you would see is a command sequence go out. In that command sequence, the NT burst size bit would not be set and the delayed burst size bit would not be set. So no data pacing. Then you would have immediately data sequences, one or more of them following that from the network controller to the network terminal. And then the network terminal, after it receives, would respond with a status sequence. So pretty obvious, pretty straightforward. The only difference is you can send a lot more data because you're on Fibre Channel and these data sequences can be really large. Next, we have the concept where we can actually use the data pacing. So in this case, you would have the command sequence, but this time in the command sequence in the frame header, you would have the NT burst size request bit set. The network terminal would receive that command sequence. The network controller would not send any data sequences. It would wait after sending that command sequence. The network terminal would respond with a status sequence. The status sequence would have the burst size acknowledgement bit set in the status sequence, and then it would have in word 7 the number of bytes that it is capable of receiving in the burst of data sequences set in that word 7 of the status sequence. Then the network controller would know how many bytes it could send in the subsequent data sequence or sequences. So then it would send those, and then the network terminal would respond again with a status sequence with the status with the burst size acknowledgement bit set again, and then also with the number of data bytes that it's ready to receive, and then on and on and on until all the data is received, and then a final status sequence is sent. So this is how you can do data pacing with the NT burst size request, and then the burst size acknowledgement and the number of bytes that the NT is ready to receive indicated in each status message as the chunks of data are sent. Then there's the second way to do data pacing using the delay NT burst size. So that's one of the other bits that's in the command sequence header. So with the delayed NT burst size bit set, what happens is the command sequence is sent, and then it's immediately followed by a data sequence up to a maximum size. So this initial data sequence that is sent because the network controller knows an initial maximum amount of data that the NT can receive based on the login that the network controller port did to the network terminal port during that port login process that I mentioned that we would talk about in a later webinar. So at a low level, at the port login level, there's some data exchanged during those logins that allow the ports to know how much data each of the ports can handle when they communicate. So the delayed burst size request, what happens with that is the originating port knows that the NT port can at least receive this much data based on the login information. So it sends it originally, but then it waits to hear back in a status message additional information about how many bytes can be received in the status sequence response. And then after that, it's basically the same that we talked about with the NT burst size request. So it's the same thing, only based on the port login information, the NC knows at least an initial data size that can at least be received in the first command, and then data sequences that are sent. Next, talk about an NT to NC transfer. So this is when the network controller is reading or requesting data from a network terminal. So on a standard MIL-STD 1553 bus, you have a transmit command sent by the bus controller to the RT. The RT sends a status word immediately, followed by the data words that were requested, and then the transfer is done. So again, pretty straightforward. On FC-AE-1553 network, you have the command sequence go out with the TR bit indicating transmit command to the network terminal. The network terminal sends a status sequence, and it can then immediately follow with some data sequences, and then it may subsequently send some optional data sequences if all the data couldn't be sent in that original status sequence plus data sequences. Pretty straightforward. The network controller indicates how much data it wants in that initial command sequence, so there's no need for data pacing because the network controller asks for how much data it wants in the command sequence. So the network controller can pace its own data by just issuing multiple command sequences. So there's not really any of the data pacing mechanism that's needed in this direction. We look at an NT to NT transfer. So if we look at how this occurs on standard 1553, the bus controller issues a receive command to the receiving NT. Then it issues a transmit command to the transmitting remote terminal. The transmitting remote terminal issues a status word, then all of the data words. And then finally, after the receiving RT receives all the data, it issues a status word. So the way this looks on FC-AE 1553 network is the network controller is going to issue a transmit command sequence to the transmitting network terminal. The transmitting network terminal will then, as a response to that, issue a receive command sequence to the receiving network terminal. Then it will issue its data sequences to the receiving network terminal. Then the receiving network terminal will respond with its status sequence. When the transmitting network terminal receives the status, it will respond to the original network controller with its status sequence. Now, there is an option in the middle here where in the original transmitting command sequence, the network controller can set a bit. There's a network controller monitor bit that can be set, basically indicating that the network controller would like to monitor the operation. If that's set, the transmitting network control or network terminal will also issue the same command and data sequences that it issues to the receiving NT also back to the network controller, so that the network controller can also see what the transmitting network terminal is sending to the receiving network terminal. So that's what this is. So summary, FC-AE 1553 is an upper layer protocol. It's the key signaling and control protocol used in high-speed 1760. It does what 1553 does for standard traditional MIL-STD 1760. It defines the set of fiber channel sequences and exchanges used to execute NC to NT exchanges. It adds in data pacing because of the large amounts of data that are transferred for NC to NT, the movement of data. So you can do all the standard NC to NT, NT to NT, and NT to NC exchanges, just like you can do on 1553. As you can see, you can do really large mass data transfers with the RDMA capabilities that are available with FC-AE-1553, and you can also see how you can do file transfers with the really large amounts of data and the data pacing that's available in there. And unlike 1553, FC-AE-1553 does not use a shared bus. So all these exchanges that I showed you can also be executed simultaneously on the network. You can have multiple nodes on the network acting like a network controller at the same time. What I showed you were individual exchanges, but you can have multiple of these occurring at the same time on the network because it's not a shared bus. And then you have a summary of the differences between the two also there in the table.